Hello guys, welcome to the next lecture. This lecture is going to be about free body diagrams, and what we mean by free body diagrams is just how to represent your forces, and then basically try and find out uh, if the entire system is in equilibrium. Try and find out if the system is at some acceleration or it is not at some acceleration. So um, if the body is disturbed from its state of inertia, which is rest, which was the zeroth state, or it's in motion at a continuous velocity, which could be also termed as zeroth state. If you're putting some external force on it, it's going to accelerate. And basically, we are going to figure out how we calculate resultant forces on a certain body, which is under consideration, and then basically try and find out at what acceleration that body is doing its motion, for example. So first we'll just look at force balance. How do we do it and things like that, and then we'll go from there. So let's say if there is a man who is standing on a plane, right, and then they are exerting a normal force which is going to be towards themselves. So along the common interface, the normal force is going to be towards themselves, and the mass of the body is towards the center of the earth. And let's say the person's mass is capital M, then there will be an exerting a force of M times G. There will be a normal force of N, and since they're not trying to jump on the weighing machine, so basically your normal force will be M times G. So uh, in case of Earth's gravity, basically if you are someone of weight, for example my weight, also somewhere around 65, then basically it will be 65 G, or basically you will say that you are 65 kg weight on Earth, right? Now, for example, if you are not standing on Earth but you are standing on Moon, where the gravity at the acceleration due to gravity is not G but G by 6, then in that case G Moon is M G by 6, which is M by 6 times G. You will be much lighter, and basically your weight will be with respect to Earth, your weight will be given as so for example my weight will be uh, you know some 10 kg weight, right? So although you were so mass by itself will be 65 kg, but your weight is not mass. It's not actually accounted for in kg. It's actually accounted for in Newton. So the unit of force is actually Newton, and and your weight is going to be accounted for in Newton. But basically we write it as kg weight, and whenever we write it as kg weight, the weight part of the thing is actually what is with respect to what is the g or acceleration due to gravity on Earth. So basically you take that g common and try to put all your parameters on the mass side of the equation, and basically you say that you are 10 kg weight. 10 kg weight still would mean that you are 65 kg person. It's just that the force will be 10 times 9.8 Newton, so you will be around 98. So you will be still 10 times, yeah, so your weight actually is around 98 Newton over there on Mars. Over here you will be 6 times more in terms of the Newton. Your mass is going to be the same, but we kind of do it in a roundabout manner. So that's why this happens. But the essential part of the problem is that we are trying to equate forces when there is no acceleration involved, specifically in the cases where the body is still in inertia. at time t equal to 0 it was in rest, at time t equal to t it was in rest, and basically you're trying to match up your forces. Alright. Now let's say that basically you're no longer you're no longer on a weighing machine which is on plain soil, for example. Now you are on a weighing machine which is moving up. So you are on a weighing machine which is moving up at an acceleration of, let's say, 2 meters per second square. Okay. So now everything has changed. So the entire system is now moving at an acceleration of 2 meters per second square, and you are interested in finding out how much how much the total weight is going to be. Okay. So in order to do this particular problem, what we'll try and do is, so I hope you guys have written this part of the problem. If not, just pause your video and take notes. So in order to solve for this problem here, so if you are solving this problem with respect to the ground observer, right, you'll see the entire system is moving up at an acceleration of 2 meters per second square, right? So basically, if that is the case, what would happen to my normal force? We have to figure that one out, right? So in the ground frame of reference, the entire body is moving up. You know, your entire body is moving up at an acceleration of 2 meters per second square. So in order to perform this calculation, what you would do is you would try to figure out what is the normal force acting on me or on that particular person. So this is normal in the upward direction. This is acceleration due to gravity in the downward direction, and the entire thing is moving at an acceleration of 2 meters per second square. Okay. So in this case, basically what you will do is that you will write this as n equals so you write this as n minus mg. So since n is in upward direction and mg is in downward direction, when you make mg positive, when you consider this direction, this upward direction to be positive, then it will become minus mg. So n minus mg equals m times a. So n will become m of g plus a. So the normal force when you are in an elevator, and let's say you are going up with an acceleration of 2 meters per second square or whatever, so that will get added to your g, which is 9.8 meters per second square, and you will feel that you are putting more weight on the elevator. Okay. You can also solve this problem if you are in, so if you are in this frame of reference, you will not feel that you are moving up at an acceleration of 2 meters per second square. What you would feel is that, so this is acceleration of elevator with respect to earth, right? But if I calculate the well, so if I calculate E of E with respect to earth is uh, A of E with respect to man is A of man with respect to earth. Or basically what you can do is you can actually think of it as a pseudo force. So basically if the entire thing is moving up at an acceleration of 2 meters per second square, you can also do it in terms of relative accelerations and things like that, but I'm not going there right now. What you will do is you will feel that, okay, now the entire thing is moving up at an acceleration of 2 meters per second square, but since I'm already inside the elevator, instead of feeling that I am uh, my thing is, the elevator is moving, because the elevator is moving and you are also moving. So basically, you will not be able to figure out at what acceleration it is moving. Sometimes it gives jerks, so you feel jerks on an elevator, but you don't necessarily feel the acceleration. You feel the change in acceleration, but you don't feel the acceleration when you are moving up in an elevator. But let's assume that if we are moving at a constant acceleration of 2 meters per second square, basically what we are going to do is we are going to figure out something called a pseudo force, and pseudo force will be acting in the direction opposite to the acceleration. So for me, or for that person over there, I'll feel a normal force of mg, and I'll feel an mg force due to acceleration due to gravity. But that acceleration due to gravity will now be compounded with my acceleration, the acceleration due to acceleration of the elevator, which is going in the opposite direction. So, so this is uh, essentially acceleration due to gravity, but a modified acceleration due to gravity. And what has happened in this particular case is that you are essentially moving up. So you can also do it in terms of relative acceleration. So basically, what you are doing is you are trying to find acceleration due to gravity. So acceleration due to gravity is a of man with respect to ground, which is a of man with respect to elevator, plus a of elevator with respect to ground, right? So that so basically what we are doing over here is that the elevator with respect to ground is plus 2j cap, and m with respect to ground is minus 9.8 j cap equals m, and this is plus 2j cap. So basically acceleration of m with respect to the elevator is becoming minus 11.8 j cap. Okay, so now you are solving this problem in the elevator frame of reference. You are trying to figure out what is the acceleration of man with respect to the elevator. Since the acceleration of man with respect to the elevator is minus 11.8 or g plus a over here, this is the force downward. It's no longer mg, it is mg plus a. G plus a being the modified acceleration due to gravity in the elevator frame of reference. And once you get that in the elevator frame of reference, that becomes a pseudo force m times g plus a, and you can equate this n equal to mg plus a, which is very different when you solve this entire problem in the ground frame of reference. So this will become n equal to m g plus a. Okay. So I guess again, please keep on asking your questions through my email. I have answered 3 questions so far, which people have asked before, and I'm planning on answering them to the best of my knowledge. Uh, so I hope this is clear to you. If not, I'm going to solve another problem. Now we'll do it in a different manner altogether. Okay, so basically now I'm going to take all this out. And basically we'll solve this in the elevator frame of reference only. Okay. So let's say instead of going up, the elevator is coming down. So acceleration of elevator with respect to ground is minus 2j cap. We know that the acceleration of man with respect to ground is minus 9.8 j cap. So we have to first figure out what is the acceleration of man with respect to elevator to make this my frame of reference, so that I can get my modified weight on the machine. Okay, so in order to do that, again, I get a of man with respect to ground could be written as vector quantity over here. Could be written as acceleration of man with respect to elevator plus acceleration of elevator with respect to ground Acceleration of man with respect to ground is minus 9.8 j cap, which we can write as minus g times j cap, g being 9.8 meters per second squared. Acceleration of man with respect to elevator, might minus a times j cap. Because this is, I'm assuming that a is 2 right now. So acceleration of man with respect to elevator will become minus gj cap plus aj cap, or minus g minus a j cap. So in order to get the force, you will put mg minus a in the downward direction for this particular man. Okay. So if I draw the forces on this particular man, we have the normal direction force, which is when the feet touch your elevator or the weighing machine, which is kept on the elevator, and assuming that the weighing machine and the elevator does not have a relative acceleration with respect to one another, we have a normal force over there, and the mg with respect to elevator, which is m times g minus a in the downward direction, n is in the upward direction. And now, since in the elevator frame of reference, the elevator is not moving at all, so basically your n is going to be m times g elevator is going to be m times g minus a. Alright. So as you can imagine from here, you can also find an acceleration when you will feel weightless in an elevator, and that would happen only and only if your acceleration becomes equal to g. So when you are coming down at an acceleration due to at an acceleration which is same as the acceleration due to gravity of Earth on objects, then you will feel weightless, and that happens when you are actually performing a free fall type of when you are going for a free fall type of a scenario in your theme park. So when you are in a theme park and you are trying to move down at an acceleration very close to acceleration due to gravity, you say it is free fall. It is free fall because you are feeling weightless, and feeling of weightlessness gives you those kind of lightness feelings. I don't like it particularly, but there are people who are crazy about it, so that's that. Okay. So this is basically what we are trying and understanding over here. Okay. And that's more or less what we are talking about for this problem. Okay, so basically you should know how to solve, how to draw forces and in different reference frames, and then once you drew your forces, you try to figure out whether there will be resultant acceleration still left on that particular frame of reference or not. Of course, with respect to ground, there is a downward acceleration of the elevator of minus 2 j cap, but then when you are inside the elevator frame of reference, there is no resultant acceleration at all, and that's what makes the problem much easier to solve for. Uh, Generally, people call these forces as pseudo forces, because in reality you are exerting force of m times g, but then because of this acceleration you are modifying this that g to g minus a for this particular place over here, and that's what I wanted to make our point clear going forward for these set of problems. Alright, so basically now this point being clear, we'll try to solve one more problem, making this point even more clear on an inclined plane, and try to also take components of these accelerations and forces. Alright, so let's do it over here. So for this problem, basically what we are going to do is we have an inclined plane. So for the first case, we are going to keep the inclined plane steady at its own place. No movement. This is firmly attached to the ground, right? And then there is a small mass m. This thing is capital mass M. And you kept a block over there. Of course, it will slide down. Assume that this is frictionless for now, this surface. Alright, so basically our intent is to figure out at what acceleration this is coming down. Okay, and basically we are also interested in figuring out what is the normal force of a small m on m, right? So as we talked about earlier, the normal force is going to be in the inward direction. So if I am standing on this floor, so the normal force, which is for my consideration is going to act towards me in the normal direction of the contact surface in between me and the ground. So first you figure out the normal direction of the contact surface between me and the ground. It could be flat surface, and if you are somehow standing on some kind of a wavy surface, that will, your feet will be on two sides of, on two of those surfaces. Basically you figure out the normal direction from there, and once you figure out the normal direction from there, figure out the inward normal direction towards you. So if you are somehow standing on a sphere, then one of the, so basically this is going to be a normal, so it has to be towards you and not towards the sphere. So these will be due to your feet 1 and due to your feet 2, these will be the two normal forces. Of course, if you are standing straight, your surface remains straight, and basically the normal force is acting towards you. Okay, so for this one, the normal force is acting towards this mass of a small mass m due to m, and then you are also exerting an acceleration due to gravity of g, due to which there will be a force of m times g. And since there is a force of m times g, let's say this is the angle of the incline at theta, you are going to exert mg cos theta in this direction and mg sin theta in this direction. So basically this is my new frame of reference for this one. Okay, I hope this is clear. Okay, if these things are clear, basically my normal force m1m is going to be mg cos theta minus mg cos theta, let's say, because n is acting like this and mg cos theta is acting like this. So basically if you consider this direction as positive, that negative sign will come there, is equal to 0, because the box is not jumping in the normal direction of the contact surface over there. So basically m1m is going to be mg cos theta, but you're not seeing any type of constraint, you're not seeing any type of opposing force to this mg sin theta in the x prime direction. So in the x prime direction, this is minus m, because the force is acting like this is minus mg sin theta, which will be equal to minus m times a, because the acceleration is also going to be in this direction. You can cancel your a's, and what you get is that a will be g times sin theta, and this is going to be the acceleration with which this block will come down if this capital mass is fixed over there. So I hope this normal force has become clear to you, this acceleration has become clear to you for this particular example. Again, this is a small example, but we know now basically how to take components. So basically, let's say whenever you are taking components either for kinematics or this type of force body diagrams, whenever there is this theta direction, you make that as cos theta, and the perpendicular one is g sin theta. Okay, so always remember this, whether it's velocity, you're throwing a ball in case of a projectile motion at angle theta with respect to you. So wherever that theta is direction is, that is u cos theta, the upward is u sin theta. Okay, and if this becomes theta, then this will become your cos theta, and this direction will become your sin theta. So always remember these small intricacies in solving problems. Okay, so anywho, with that, I would say basically we now know how to resolve our forces based on based on we know how to resolve our forces, we know how to solve for the forces in two directions of the same coordinate system, in inclined coordinate system, for example, in this problem as well. So I think that's pretty good. Let's move on to a case where this capital mass. So I hope I'm going to give a minute, probably half a minute, and then I expect you to take notes. If you have not been able to take notes, just pause the video over there and basically start taking notes on that particular one if you want to. So let's go ahead. Uh, Solving another problem. Now what's happening is over here is this capital M, let's say, is moving at an acceleration a capital M due to gravity value towards its right hand side. Now my mass is kept like this, alright? And now basically I want to find out what is my acceleration of M on M in the reference frame of M. So basically it's moving like this and you are also going down. So you are going down like this, and looks like your escalator is moving back. So you are trying to figure out, you know, what is your acceleration with respect to that moving escalator, which is moving towards your right. So you have to be very careful with respect to this problem. Okay, so this being the case, again, what we are going to do is first figure out um, how we can actually solve for this problem, right? So that is very, very important, how we want to solve for this problem. So again, there is this definition of pseudo forces which we have been discussing over and over with respect to solving these problems, and that kind of becomes a reality over here, right? And you are trying to figure out, how I'm going to solve this problem after all. So that is pretty interesting actually. So anywho, so first of all, this is acceleration of capital M with respect to gravity. This is, let's say this is theta. So this is going to be theta. So you resolve this. So since theta is in that direction, A of M with respect to G is going to be cos theta in that direction, and A of M with respect to G sin theta in this direction. Now remember, in pseudo forces, what happened was, if you are going up at an acceleration of 2 meters per second, when the force was getting calculated, it was becoming mg plus a in the opposite direction, right? So if there is an am with respect to g cos theta in this direction, there is going to be an additional force of am with respect to g cos theta in this direction, okay? Also, if you resolve for G has a cos theta component, G sin theta component. The G sin theta component will have a force of mg sin theta also in this direction. So if this is y prime and this is x prime, basically in the negative x prime direction, you are going to have two types of forces. One is mg sin theta plus m capital A with respect to g cos theta, entirely negative because the force is entirely in negative x prime direction, equals minus ma small m with respect to capital M. So my A small m with respect to capital M, and now this is only the x component of it, because it could have a y component, right? Could have a y component, but we know that in that frame of reference it's not it's not going anywhere. So it is going to have only this component, because in this frame of reference, in the capital M frame of reference, this box is not moving up or down. All right. So basically, in that y prime direction, there is no resultant acceleration. In this direction, there is resultant acceleration. So am with respect to m in the x prime direction is actually am with respect to m, because this is the total acceleration, and that is going to be negatives will cancel, because both of them, the acceleration, the resultant acceleration and the forces are both in negative x prime direction, is going to be g plus a m with respect to g cos theta. And if you want to figure out what will be the box's acceleration in the ground frame of reference, which is generally the question, what you do is am with respect to capital M plus am with respect to g. So this g plus a cos theta is in this direction. So okay, so and am with respect to g is in that I cap direction. So basically, this is am with respect to m. So if this angle is theta, then because these are two parallel lines, so this angle is going to be theta. So wherever that theta is, that will be cos theta. So basically, this will become g plus am with respect to g cos theta, and then the cos component of it, which is in the negative I direction, I cap direction, plus am with respect to g, which is in the positive I direction. So this is going to be minus g cos square theta I cap plus am with respect to g 1 minus cos square theta I cap. So this will become minus g cos square theta I cap plus this is a small m with respect to g, this is capital M with respect to g, sin square theta I cap. So this will be the acceleration of am with respect to ground in the x direction. Similarly, in the y direction, since this is the total acceleration, this is going to be a small m with respect to m cos theta, but then am with respect to g is all in I cap. So if I am trying to write am with respect to g in the y, then it is am with respect to mass m in the y direction, which is downwards, a capital M with respect to ground, a capital M with respect to ground in the y direction. So this is all calculation for the x direction, which we did here. For the y direction, am with respect to ground in the y direction is 0, or plus y, whatever, in this entire vertical plane is 0, or vertical direction is 0. So a small m with respect to ground y will be sin theta, a small m with respect to capital M sin theta, where this is the value of theta, this is the value of am with respect to m. So this is g plus am with capital cos theta sin theta, which you can write it as sin 2 theta divided by 2 cos theta sin theta. So yeah, once you get the small m with respect to ground acceleration in x direction and y direction, you have solved for this problem. Now for the normal forces, we have solved only in the x prime direction, this particular body. So we are going to solve for in the y prime direction as well. Again, I'm going to give you like 10 seconds pause over here. And hopefully you can take notes. If you want to, you can again, because it's a video, you can again pause the video and take notes wherever you want to. Okay, so with that we are moving forward. and we'll try and figure out what will be the acceleration, what is the normal force in the y prime direction. So in the y prime direction, in the capital M frame of reference, we know for sure that the boss, that is this is small body, small m, is not jumping on top of it. So this is going to be n, but now since I have a component in this direction, there is going to be an opposite pseudo force am times g sine theta also in the normal direction, and then this force, which is due to g cos theta, will be in this direction. Okay, so we take the positives as positives and negatives as negatives, n plus m with respect to g sine theta minus m g cos theta equal to 0. The sum of positives and negatives is 0 because there is no resultant acceleration. The box is not moving up and down on this capital M in the capital M frame of reference. So my n is going to be m with respect to ground sine theta. I take that small mass common plus g cos theta. So with that, we can calculate the normal force and using the pseudo force method in this capital M frame of reference. Once you have calculated this in the pseudo frame, basically it will also remain the same in the ground frame of reference. So about forces, you don't have to worry about accelerations, you have to worry about changing their frame of references accordingly. Okay, so with that, I'm going to solve a problem which one of you guys have asked. I think this problem is taken from David Morin, and this problem is on projectile motion. Again, I'm going to give you guys like 10 seconds to take down notes if you want any on this particular problem. Again, you please feel free to pause the video and take notes whenever and wherever inside the video you want to. So you're free to do that. All right. So one of the guys has asked a problem. So I'm going to do that. And then there is another problem which I might have time to do today. Okay. So let's see. So yeah, the first problem is basically if you have, let's say, thrown something at theta equal to 45-degree angle, it covers a certain range, and then basically you have thrown the same ball or a different ball, because in kinetics the mass does not matter, at another theta angle, and then basically you have two identical, so basically this ball covers a range of r by 2, and then basically elastically keeps the same momentum, and then does another projectile motion. So in two projectile motions it covers the same amount of range as the first projectile did at an angle of theta equal to 45 degree. Okay, so I think this should be absolutely clear. So first, don't worry about the second projectile motion, don't worry about all the theta and whatever. Okay, so first one is theta equal to 45 degree. Don't worry about the 45 degree. We'll first get the thing in general, and then basically you know, put in theta equal to 45 degree as required. So first of all, since this is a symmetric easy projectile motion, the time to go from here to here is going to be t by 2. So basically, in order to trace down this path, is t by is if the total time of travel is t, then going from here to here is t by 2. Okay. Now simply assume that the velocity is u. This is theta. So basically, you're talking about u sine theta, the upward direction, and again you see that since theta is subtended towards with respect to horizontal, you write it as u cos theta in the x direction. Now basically you know that the maximum height this is also the point of maximum height, and whenever the maximum height gets achieved, your v becomes equal to 0, or the final velocity becomes equal to 0. You can put this first equation of motion in the plus y direction. So your this is going to be 0. The initial velocity is u sine theta positive j cap. The downward acceleration is g j cap, but it's a negative, minus g j cap times t. Let's say we know that this is going to be half of the total time because it's symmetric projectile motion. So basically, total time of flight will be 2u sine theta over g. See over here, I did not use t, I used t by 2, assuming that the total time of flight is t. So the time to go from here to here is t by 2. Okay. So the total time of flight to do the entire projectile motion is t equal to 2u sine theta over g. Then we can calculate the arc in the horizontal direction. In order to do that, we'll have r vector equals u vector times t plus half a vector t square in the horizontal x direction. Now we know in the horizontal x direction, because it's a simple projectile motion and not at an inclined plane, your acceleration due to your acceleration in this direction is 0, right? It's not like minus gj cap is acting and pulling it downward. So this is going to be 0, and my initial velocity is u cos theta j I cap, and then my time is 2u sine theta over g. So over here my r vector is going to be 2u square sine theta cos theta over g, or you can write this as u square sine 2 theta over g I cap. So there is an I cap over here. Okay. So once we get the range vector, then this is absolutely easy. You can put theta equal to 45 degrees, and once you put theta equal to 45 degrees, sine 2 theta becomes 2 theta becomes 90, or sine 2 theta, you can directly put sine 2 theta equal to 1, and this becomes u square over g I cap, which is your range vector for theta, for the special case when theta equal to 45 degree, right? Now you see the general formula over here. This is 2u square sine theta cos theta over g. And basically what our friend was talking about is that there are two projectile motions which covers the same distance in r by 2 notion. So if this is my r vector, so for two of these ranges, so basically at a different theta angle, let's say theta 1, I'll have 2r theta 1, which is 2 times this 2u square sine theta cos theta over g, or u square sine 2 theta over g I cap. That should be equal to this range when the theta angle is 45 degree, which we know for the special cases given by u square g I cap, right? So if that is the case, then 2u square sine 2 theta over g is u square over g, and your sine 2 theta is becoming half. When sine 2 theta becomes half, means 2 theta, this argument of sine, is actually, let me think about it, is actually 30 degrees, and your theta is actually 15 degrees, right? So when theta equal to 15 degrees, you can thread the projectile, and if it elastically rebounds, then you'll have uh, two of those ranges of that projectile will be equal to the range which you can achieve by 45 degree angles. So again, it also shows a very little concept. It's not about the quantity, it's always about the quality. It's more philosophical, which I'm going in here, but that's true. You have to believe in that whenever you hire, or whenever you will become or go in a position of hiring, always hire quality, never the quantity. You can see what you can get done with two people, you can get done with one person if he is of high quality. Okay. Anywho, so that's a philosophical comment at the end of this lecture. I hope you guys do good and you have a great time ahead, great week ahead. Thanks for your time. Thank you. Bye.